So let me say that in order to give this presentation, I'm going to present some slides that Klaus Pontoppidan presented at another meeting. I actually have slides that Jason presented, but I liked Klaus's better, so I'm going to show Klaus's. He's the deputy project scientist at JWST, and he was heavily involved in making the exposure time calculator. So I'll put a little bit of infrastructure in, but I won't show anything more because Diane's going to do a demonstration, and it's not in my presentation anyway. So. And I guess I'll also give the disclaimer. Yeah, it's the last slide. That these are the purpose of this talk is to show the tools that Space Telescope is working on or has put out there, and then we'll see some other talks about tools that are put together by the team. Right, and I'm supposed to stand here. I remember now. The audio is coming from here. So just to repeat that for Webland, so I'm presenting some slides that Klaus Pontoppidan put together. Showing the tools that that we're working on at Space Telescope. So here's the list. There's the APT, which you've heard about, the exposure time calculator, which you've heard about as well, and data simulator, singular, I think is correct, calibration pipelines, which Carl will talk about after me, user documentation, show you what we're doing there, and data analysis tools, I think, is the last slide, the last topic that we have in the presentation. So APT, you've seen bits and pieces of this. I just want to say it's easy to download, easy to install, easy to try. It's got maybe 80%, let's say, to pick a number of the capabilities that it will ultimately have when you have to submit, push submit. Some things are complete, other things are less complete. But if you want to get some experience, you can do that now. And I had talked about templates already, so Klaus wanted to just reinforce this same point that instead of specifying filter, move, exposure, dither, things like that, you fill in high-level parameters. And as I said in earlier talks, there's 16 science templates, 4 for each instrument. And once you've filled out your parameters, as it says at the bottom of this slide, the observation is broken into 1 or more visits. All right? And then those visits get scheduled as separate entities, perhaps back-to-back, perhaps not. All right, exposure time calculator named Pandeia, the Greek goddess of calculating exposure times, in case you're wondering. So they actually did a lot back there in ancient Greece. We don't often appreciate that. So there's 4 logical blocks here. There's the reference files that have describe the performance of JWST and the instruments. There's an engine, which is a separate entity, and in fact can be downloaded. So this is a nice feature of the architecture that if you want to do your own exposure time calculations and you know some Python, you don't have to try to do some weird thing through the web interface. You can just download the engine and figure out how to use the engine and the reference files, of course. There's a server, which you'll see that the exposure time calculator, you actually will have an account, and you can have workbooks, and I'll show you that in a minute. But there's a server that stores all your calculations. And then there's a user interface, which is a web application. So it runs locally in your browser, and it calls the server, which calls the engine, and so forth, right? So that's the architecture. It says here the development release of the engine is spring. That has happened. And in fact, there is a development release of the user interface as well. So the development version is out in the wild. You can find it just by searching in Google. And then the official release, after we've shaken out bugs and things, will be in January of next year. This is the workbook concept I was talking about. So you can share your workbook with your collaborators. So that's kind of cool, right? You guys, somebody, let's say hypothetically, a graduate student starts the calculation, and then somebody else can come in and look at it and modify it or whatever. All right, simulator, singulars. So we are working on a project called STIPS, which is the Space Telescope Image Performance Simulator or something like that. What is it? Project simulator, that's what it is. The sad part, well, I won't share the sad part, is the guy working on it was in my group. Doesn't mean I remember the acronym. So the idea is, let's see, I don't think we have the interface. So this is not out yet, so you can't go use this yet. But you specify astrophysical things about cluster properties or something like that. So this scene has 4 clusters that have been artificially generated in it, and it understands what the NIRCam and MIRI imager fields of view are, and it can generate images, simulated images like that. It's not a high fidelity simulator, so it doesn't have, I don't think it has the image distortion in it, but it gives you a sense of what JWST, it does use the web PSF tool, and so you get a sense of what the star fields, what data might look like. So that will be helpful for visualizing what sorts of things will be possible. So the web, changing gears a little bit, it's not really a tool, but documentation. So with JWST, we have taken a bold step for ourselves in how we're going to do documentation. We, in the past, for HST, have done monolithic documents, instrument handbooks, and the assumption was when you get to the description of a grating that you've read everything that came before about detectors and whatnot. We're instead going to go with articles. The philosophy that sort of motivated us is this book, Every Page is Page 1 by Mark Baker, where you imagine somebody does a Google search for I want to do IFU spectroscopy or whatever, and they wind up on some article, much like Wikipedia. And if it isn't exactly what they wanted, it at least is very close, and a link from that page would get you to where you want. But each page has enough context. It's at one level. You can dive deeper, you can go back up or whatever. So it's taken us quite a while to get our head around how to divide up the information in this way, because that's not the way we have done it in the past. But we have our platform set up. We have our workflows for creating articles. We have a bunch of draft articles in various stages, and very soon we're going to roll that out. Also, at a higher level, we are making website changes. So in our mind, inside our building, there's a distinction between these documentation pages and then just higher level website that has broader information. So they have the website, which that is out. You will find that has the calendar of events and other things. So this is our work on documentation ongoing. Articles will be coming out soon, and then coming out progressively as we write them and review them. Data analysis and visualization tools. So we have pipelines that do processing, initial processing, and then in our jargon we have tools that astronomers will use to analyze the data products that are generated by the pipeline. We are trying to build on and support AstroPy and build on top of it additional tools. So it's Python oriented. We're not going to be doing STSDAS or PyRAF implementations for JWST. The visualization, as it says, will be with Ginga and Glue, which are tools that are out there already. We'll make sure that the tools understand JWST data structures. And so the code that we have developed along these lines so far is available. It's open source. It will be open source throughout the project. This is a timeline. The development process that we're using for these data analysis tools is a sprint development approach. So we take an expert astronomer or 3, and we put them in the room with the developers who are going to work on the task. And they define what are we going to do in the next 2-week period, and set up some goals. And then they iterate. The user says, "Well, I really want this." The developer says, "That's super hard." And the astronomer says, "Well, how about this instead?" The developer starts and says, "I could give you this other cool thing." And having the people right there in the room makes the right tool come out at the end and come out in a quick fashion. It requires focus for a couple weeks, but it's a very good way to get the right thing out in the end. These are the ones that have happened, I believe, at this point. So there are things like PSF tools, synthetic photometry, MOS tools, polarimetry, stuff like that. Photometry, sorry. This is ongoing work. If anybody is interested in getting involved, just let me know and I'll hook you up with the right people. If there's a particular topic that you think JWST should have a tool for, a really good way to get us to work on it is to volunteer to be involved in a sprint to work on that type of thing. I'm just saying, not that you would do it on your own, right? But we need experts in a certain field in order to be able to do the right thing in those tools. And this is just an example of the cube viewer, but it's a PDF, so I can't show you that. And then for my last slide, so this is the tools on a schedule. So the ETC engine release, and indeed the interface, the development version, has come out. The first release of the documentation is not yet happened, but is very soon. The official ETC on the web, the flight release, as we call it, will be in January of 2017. There's actually going to be multiple versions of APT coming out before the GEO deadline. A particular one is highlighted there. There'll be 3, actually. And then you have but this one that's being highlighted is the one that would be used for the early release science deadline. And so that's actually two releases from now. And then there's a GEO call for proposals and launch and all that. So I'll stop there.